Hi guys, this is Mr. Gron, 6.5 day 2, finding real roots of polynomial equations. You will need a calculator today. We're really going to lean on, build on what we did yesterday using graphing and synthetic division to solve polynomial equations, and we're going to throw in some quadratic formula as well. So our first set of problems are some box problems, some geometry applications, and we'll see these again in pre-calculus. But for right now, read the problem, pause and read the problem, and when you're done, unpause it, and we'll go through it. All right, so the idea here is that we have some equations that give us the various dimensions of the box, and we know what the volume is, so we need to work backwards and figure out what the dimensions are based off of all of this stuff that we're given. So the volume of a box, length times width times height, so that's going to be x for the length, x minus 2 for the width, and x plus 5 for the height, and it is equal to 24 cubic inches. Now, what you could do is start foiling everything out, multiplying, and making a polynomial, then subtracting 24 from both sides and trying to factor it and that stuff. But what we're really going to just do is use the graphing calculator to solve this. So I'm going to subtract the 24 from both sides, and this is going to be x times x minus 2, x minus 5 minus 24 equals 0. And this is what I'm going to plug into my graphing calculator. All right, so I've got it in my graphing calculator, and it looks just how it looked before. I'm using Desmos. Obviously, you'll use your TI-84s. But looking at the graph, I can see that I have three solutions, one of them here at -4, then at -2, and then at +3. And the +3 is going to be the one that we want. Obviously, these aren't going to have negative lengths and widths and heights and stuff like that. So these two don't really make sense. This is the only one that does make sense. So then, according to our graphing calculator, what is the length of the box? The length of the box was 3 inches. Oops. All right, this is basically the same thing, only now we don't have a diagram, so we have to build it ourselves. Now you can try this, pause it, and then come back if you'd like. Otherwise, let's see, we know that it is going to be 12 cubic feet is the volume of our box, so 12 is going to be on one side. Width should be 1 foot less than the length, so one factor is going to be x minus 1. Let's see, the height should be 4 feet greater than the length, so that's going to be an x plus 4. And then we need to know what the length is, so the length we're going to say is x. Now, same thing as before, we're going to subtract the 12 from both sides, and this is what we're going to plug into our graphing calculator and solve for where it equals 0. So on our graph, we've got, again, two negative solutions that aren't going to make sense for this. The length of it is not going to be -3 or -2. It's going to be the +2 from over here. So the length of our crate should be 2 feet. One more to pause, try it on your own, basically the same thing. If you got this, you should be ready for the homework. So going through this piece by piece, let's see, we've got a length that's 3 feet longer than the width. So that's going to be x plus 3. The height is 1 foot longer than the width. So that's going to be an x plus 1. The volume is 30 cubic feet. And we don't know what the width is, so I need to throw in an x for the width. So the x is going to be the width this time instead of the length. Same thing, we're going to plug this into the calculator. +3 plus 1 minus 30 equals 0. And now in this case it's a little simpler because I only have the one solution here, and that is here at positive 2. Now one thing I should mention, a question that you might have had at one of the earlier problems is, why are the solutions not 0, -3, and -1 from these factors? And the answer to that is, this isn't the factored polynomial. Because of this minus 30 here, it makes it so these don't necessarily account for the zeros. 2 is the only thing that if I plugged it in for here into this x and to this x, this whole part would equal positive 30, which would then get canceled out by this negative 30. So this is not in the fully factored form, and that's why these three things aren't directly where the solutions come from. All right, so rational root theorem. This is a theorem that gives us possible rational solutions to polynomials. And where this is going to be useful is when we get ones that aren't right on whole number grids. So your 2's, -1's, whatever. The ones that are going to be at like 3/4 or 2/3 or some fraction, some rational number. It gives us an idea of where we're going to look. So what it says is, if we know what the polynomial is, p is the constant, or are factors of the constant, and q are factors that come from the leading coefficient, which is kind of backwards if you ask me. It really should be that this is p and this is q, but it's opposite. This one is q and this one is p. All of the rational roots are going to be a combination of factors of the first and last number. And so listing the possible rational zeros from our cubic polynomial here, I could say that for p over q, that this is going to equal all the positive and negative possibilities from the factors of 6, which are 6, 3, 2, and 1, and of 2, which are 2 and 1. So the actual list is going to be this, plus or minus for all of these. Now I let students just put a 1 plus or minus at the beginning and then list out all the numbers. Not every teacher is going to be the same. And now it's all of the different combinations of these numbers. So 6 over 1, 3 over 1, 2 over 1, and 1 over 1, all the whole numbers from the top. And then all of the numbers over 2. So 6 over 2, 3 over 2, 2 over 2, and 1 over 2. Now, you might say, Mr. Grahn, you need to reduce your fractions, and you're absolutely right. So for your answer, you should eliminate all of the repeated ones. So 6 over 2, for instance, this one we can cross out because it equals 3, and I already have that here. And then 2 over 2, we can cross that out because I already have 1 over here, which is an equivalent. So your final answer, we don't want those two, just these ones. All right, our next thing is the irrational root theorem, which says that if a plus the square root of b is a solution, that this is a solution if and only if this is a solution, the conjugate, so it's a plus the square root of b and then also a minus. They always come in pairs for polynomials. Where this is going to come in handy is, or what I'm going to ask you to do with it, is to identify conjugates. So if I give you this one as a solution, that you would regurgitate this as a solution, and vice versa. All right, so now the first really large problem where we're putting everything together, identifying all the real roots of this rather intimidating looking polynomial. The first thing that we're going to do is use the p over q stuff to just get an idea of what we're looking for on the graph. It's going to turn out that this is going to have some solutions that are fractions, not all just whole numbers. So we want to know like where we should probably look for them. So our P over Q is going to be plus or minus all of the factors of 6, because it's the very last number, so 6, 3, 2, and 1, over 4, our leading coefficient, so 4, 2, and 1. And those are all of these. So we've got some whole numbers that we can look for, and then we also have some fractions here that we can look for in the graphing calculator. So let's go ahead and plug that whole big ugly mess into the graphing calculator and see what happens. All right, so here's our polynomial. It's got 4 real zeros, so we're gonna have 4 answers. And if I look at this, I've got 1 at negative 0.75. Well, that's negative 3/4. That was one of the fractions that we thought it could be. 0.268, that's not going to come from one of those fractions, so this one must be irrational. 2, that was one of my possible rationals, so that one makes sense. And then weird decimal numbers, so this is going to be an irrational. And for those 2 irrational ones, we're going to have to use the quadratic formula to figure them out. So my 2 zeros, real rational zeros, were negative 3/4 or negative 0.75 and positive 2. So those are going to be where I start when I'm using synthetic division. Now, it doesn't technically matter which one we start with. It's always going to be easier, though, at first to start with the whole number. So 2 is going to go on the box. Then my coefficients, 4, negative 21, 18, 19, negative 6. Bring down the 4. 2 times 4 is 8. Negative 21 and 8 is negative 13. 2 times negative 13 is negative 26. That's going to make negative 8. Negative 16, excuse me. That'll make positive 3, and then 2 times 3 is positive 6, so we have 0 as a remainder, so that's good. Now I can take out the negative 3/4, and if you want to use negative 0.75, that's fine too, it doesn't really matter. Now all the numbers now, incidentally, are smaller, so the coefficients have gotten a little bit smaller and there's less of them, so less multiplying by a fraction, which I think most people think is a good thing. I don't necessarily, but that's just me. All right, so the 4 comes down. Negative 3/4 times 4 is negative 3. So that's negative 16 times negative 3/4 is positive 12 times negative 8 plus 12, positive 4 times negative 3/4 is negative 3, and I end up with a 0 again, so 2 good factors. Now what I have left is the polynomial 4x squared minus 16x plus 4, and I immediately see that there is a greatest common factor here. They're all divisible by 4, so I'm going to take out that 4 at this point and say that this is 4 times x squared minus 4x plus 1, which is going to be an easier polynomial to work with this quadratic in the quadratic formula. This does not factor, and so this part right here, I'm going to use the quadratic formula to figure out. I've got 2 solutions. To get my other 2, I'm going to plug this unfactorable quadratic into the quadratic formula. And I'll do that. I'll kind of partition this. So A is going to equal 1. B will equal negative 4, and C will equal positive 1. So negative of negative 4 is positive 4 plus or minus the square root of negative 4 squared minus 4 times A times C all over 2A. Starting to reduce this a little bit. 4 plus or minus the the discriminant in this case is going to be This part is 16 minus 4, so that's the square root of 12. So 4 plus or minus root 12 all over 2. Root 12 reduces. This will be 4 plus or minus. I can factor out of here a 4 and a 3. The square root of 4 is 2, so the 2 comes out, and the square root of 3 stays in. It's still all over 2. And now everything reduces by a factor of 2, so the 4 divided by 2 is 2, and the 2 cancels out with the root 3, and so it's 2 plus or minus root 3. So that's going to be negative 3/4. Our solutions are negative 3/4, 2, and 2 plus root 3 and minus root 3. So looking back at our graph, we had negative 0.75, that was the negative 3/4. This 0.268 would be the 2 minus root 3. If you plug that into your calculator, you would get a decimal number that would round to that with 3 decimal places. We had negative 2, or positive 2, and then this would be your 2 plus square root of 3. All right, this one is a little bit simpler, so try this one on your own, pause it, and then see how Mr. Grahn does it. Now, P over Q to start with. This is going to be plus or minus all of the factors of 4, which are 4, 2, and 1, over the factors of 2, which are 2 and 1, and that's going to be equal to plus or minus 4, 2, 1, 4 over 2 is 2, 2 over 2 is 1, and 1 over 2. So not quite as much stuff to look for. Looking in the graphing calculator, I've got one rational, negative 0.5, that'll be negative 1/2, and then 2 what would appear to be irrational solutions. So I know negative 1/2 is a good solution, so I'm going to take that out of here. 2, negative 3, negative 10, negative 4. Negative 1/2 times 2 is negative 1, negative 4, positive 2, negative 8, positive 4, 0. And so I have a quadratic that again has a greatest common factor. So 2x squared minus 4x minus 8 is what I have left. We'll pull a 2 out. X squared minus 2x minus 4. Again, non-factorable, so I'm going to have to go to quadratic formula. A is 1, B is negative 2, and C is negative 4. So negative of negative 2 plus or minus square root of negative 2 squared minus 4 times 1 times negative 4. Be careful with your negatives on these ones. All over 2a. That is going to be 2 plus or minus the square root of, this will be 4 minus negative 16. So 4 plus 16, which is 20. So 2 plus or minus root 20 over 2. That 20 factors to 4 and 5. So that means this will be 2 plus or minus 2 root 5 all over 2. And all the 2's cancel out, and it's 1 plus or minus root 5. So the 1 plus or minus root 5 give us our 2 weird decimal ones. So our solutions are negative 1/2 and 1 plus or minus, 1 plus root 5 and 1 minus root 5. And one last one. Again, P over Q plus or minus the factors of 2 over the factors of 2. So not a lot to look for again there. It would be 2, 1, and 1/2 plus or minus. So looking at this one, I've got 2 irrationals, weird decimal numbers, and one nice rational number, 0.5, which would be positive 1/2. So I know 1/2 is good, so I'm going to take that out. Remember, you need a 0 for the missing power of x. So this is 2, 1, -8, -4, -4, -2, 0. Again, have a quadratic that has greatest common factors. So that's going to be 2 times x squared minus 4x minus 2. Very similar looking to our last one, but not quite the same. A is going to equal 1, B -4, C -2. So negative of -4 is +4, plus or minus square root of -4 squared minus 4ac all over 2a. That will be 4 plus or minus the square root of 16 minus -8, which is 16 plus 8. So that's 24 all over 2. 24 factors 2. Let's see, 4 and 6. 4, the square root is 2. So this is 4 plus or minus 2 root 6 over 2. And that's going to reduce to 2 plus or minus root 6. And so our solutions, 1/2 and 2 plus or minus root 6. There's the homework. Give it a shot. Come with some questions tomorrow, and we will wrap up the last new topic of semester 2.